calculating the standard change in free energy for a reaction. That is what the criterion for spontaneity is. It's delta G. Delta S can kind of give us an idea, but we've got that interplay between delta H and delta S. So delta G is what we really need to be looking at. There are 3 different methods that you can use to calculate delta G. So we're just going to look at the first one today, and we'll save the other 2 for Wednesday. So we can calculate the change in enthalpy for the reaction and the change in entropy for the reaction from standard heats of formation and standard molar entropies, and then plug those into this Gibbs free energy equation. You can also calculate it directly from the free energy of formation, and you can also calculate it from the free energy changes for the individual steps in a stepwise reaction. But we'll deal with those later. Okay, so we need the change in entropy for the reaction, and we need the change in enthalpy for the reaction. This equation is what we just learned about, right? So we should be okay on that. Calculating delta H, it's the same pattern. It's the same type of an equation, but you're just going to look in the delta HF column in the same table. Okay? So it's really not that bad. So we need to calculate the heat of reaction and the change in entropy for the reaction, and then we need to know the temperature to do this. Now, strictly speaking, it's only valid at 25 degrees Celsius because the heats of reaction and the changes in entropy change somewhat with temperature. But they're not super temperature dependent. And the temperature changes that we're usually talking about are relatively small because this is in Kelvin. And so we're going like from 273 Kelvin, which is the freezing point of water, to 298 Kelvin, which is room temperature, right? So the changes are not huge. So it still makes a good estimate, but strictly speaking, it's only valid at 25. So a couple of examples. Consider the oxidation of NO to NO2. So here's the equation. What is odd about that chemical equation? It's got a 1/2 in it. That's okay. When we deal with heats of formation, a heat of formation is always calculated to produce 1 mole of product. Okay, so that's why these are always going to be ending up with 1 mole of product. So we need to calculate delta G at 25 and identify if this is spontaneous or not. So we need to calculate the delta H and delta S. So I'm going to make a little table under my chemical equation. We need, let's do this one first. We need delta H, standard heats of formation, and we need standard molar entropies for both of these. I'll stick that over here. See if I can line it up. These are going to end up being in kilojoules per mole, heats of formation, and these will be in joules per mole Kelvin. So we'll have to watch out for that. So we're looking in our table again. NO. NO in the gas state, delta HF is 91.3. 91.3. And as long as we're there, we might as well get S to 10.8. And oxygen, O2. Delta H, the heat of formation for oxygen, is 0 because that's in its standard state. So that's 0, but its entropy is not 0. It's 205.2. And then we look up NO2. Heat of formation is 33.2, and the entropy is 240.1. So now we're going to calculate, I'll just do delta H first, the change in enthalpy for the reaction. We're going to take the heats of formation for the products, here there's only one, times the coefficient, and we're going to subtract the heats of formation for the reactants times their coefficients. So we end up with 1 times 33.2. Then we're going to subtract 1 times 91.3 and half of 0. This one is 0. So that ends up being kind of simple there. Except the first time I did this at home, I did it wrong and came up with the wrong number, and that messed everything up. So this ends up being minus 58.1. What are the units on that? Kilojoules. I'm being sloppy and leaving out units, but I think you guys can handle it, right? This number was 1 mole of this times 33.2 kilojoules per mole. And so this is kilojoules, that's kilojoules, and we end up with the unit of kilojoules. Delta S for the reaction, same idea. So we've got 1 times the entropy for the product, 240.1. And we're going to subtract the reactants. So we've got 1 times the entropy of NO, 210.8, plus half of the entropy for the oxygen, 205.2. Just be careful when you communicate with your calculator that you're putting it in correctly. So 240.1 minus the quantity 210.8 plus 0.5 times 205.2. I'm getting minus 73.3. What's the units on that? Joules per Kelvin. Because again, we were multiplying by number of moles, so the per mole part went away. Does it make sense that the change in entropy is negative? Yeah, because here we have 1.5 moles of gas, and here we only have 1 mole of gas. Fewer moles of gas, lower entropy. So now we can calculate the standard change in free energy. Delta G standard for the reaction. It's delta H, which we found to be minus 58.1 kilojoules. Now, I'm going to just change that to joules. And then that's minus the temperature, which is 25 degrees Celsius, so 298 K, times the delta S. So that's minus 73.3. And that'll be joules. I canceled the K's out. I'm sorry, I'm being really, really sloppy with my units. Don't tell my 3A students. So minus 58.1 times 10 to the third minus 298 times negative 73.3. Negative 36256.6 joules. So we should probably put that into kilojoules, negative 36.3 kilojoules. Did I do my math correctly? Anybody actually punch it through on their calculator? Yes? Is it spontaneous? Yes. See, yeah, there almost needs to be the pause there where you're like, things going down the hill, right? To get it straight. And that's perfectly fine. I have to think about it myself. So this is spontaneous at this temperature. Is this one where the spontaneity depends on the temperature? Yeah, because delta H and delta S are both negative. When the signs are the same, the temperature is important. If the signs are different, the temperature is not going to matter in terms of whether it's spontaneous or not. Now we're going to estimate the standard change in free energy for a reaction occurring at some other temperature. This is just an estimate. So we're going to use the reaction in the problem that we just worked, and we're going to calculate the value of delta G at minus 55. And we're asking, is the reaction more spontaneous or less spontaneous at the lower temperature? And for our convenience, I put the delta H and delta S that we already calculated, right? Because we don't need to do that again. So delta G for the reaction. This is the same calculation, but the temperature is different. So here we have our delta H, joules, right? And this is minus, what's the temperature? Negative 55 Celsius, but that we need to put it in Kelvin, 218. So this is 218 Kelvin. I'll put my units in this time. And that's times delta S, which is minus 73.3 joules per Kelvin. So the kelvins cancel out. So we have minus 58.1 times 10 to the third minus 218 times negative 73.3. So that's minus 42120.6 joules, which is minus 42.1 kilojoules. More or less spontaneous. The other one was minus 30 something, right? 36?
More spontaneous.
So this is more spontaneous because it's more negative. The change in elevation for the boulder rolling down the hill is greater. It's more spontaneous. Any questions?